Hello, this is Brian Kinghorn, and I'm going to talk to you about managing trait distributions using MateCell. And this is the third of 3 videos in this series. We've already looked at standard operations and advanced operations, and now we're going to ask whether we should manage our traits in the first place. So we're going to look at 3 components here. One is looking at changes in the distribution mean among the progeny for some traits. Then we're going to look at changes in the distribution shape for some traits, for example, to reduce variation in predicted genetic merit. And finally, we're going to look at managing genetic variation for some traits, for example, that we might want to be maintaining genetic variation for some traits that we're concerned about. So first of all, changes in the distribution mean. So basically, we're looking at changes in the direction of genetic change, whereby we might want to ensure that we have a higher level of response in a given trait compared to what the default would otherwise give. And you'll see in this yellow box that we have a number of tools in MateCell that we can use to effect changes in the direction of genetic gain, the pattern of genetic gain. But we're not going to look at that here. We've already done that. Here we're asking the question, should we do it? And under what circumstances should we do those things? So should we trust our economic and index weights? Generally, quantitative geneticists would say yes, don't mess with those, just use them and go straight ahead. Is it possible that the weights have been calculated without all the information available? For example, they might have been calculated assuming economic rationality and that the production efficiency must be improved, and yet you know that your seed stock customers might not be happy with that outcome. They may not be economically rational. They may, for example, be more concerned about animal welfare, and that might not have been taken account of appropriately. Then we've got the possibility of unrealistic assumptions made, and we'll talk about linearity in the example coming up. Lastly, and probably most important, is that large desired changes may be possible with little damage to the predicted overall economic response. In MateCell, that's seen as reflected on how close the solution is to the frontier. So we'll explore these last 2 components with a simple example. So we're going to use some other software to make some illustrations here. You can search for GenOp on the web. What we're looking at here is the predicted genetic response we can make for 2 traits, lean percent and number born alive in this example. And these are from prediction formula, not from ABVs of individual animals. So these are theoretical predicted responses. And by altering the relative economic weights between those 2 traits, we can be anywhere on this yellow ellipse. So we start at the very origin here, and within, say, 10 years' time, we could be anywhere on this yellow ellipse by using different selection index policies. The current index solution is over here, and that makes sense because if I show the isoeconomic lines, anywhere along this line here, for example, is calculated to be of equal economic value, no matter what the combination of traits are. So there's your linearity. And of course, with number born alive and lean percent, well, you would think that that should be multiplicative because the best thing to do is to have a combination of both, and that these might curve outwards here a bit, and generally selection indices don't take account of that. That's not a critical issue though. Let's switch those off and consider what would happen if we reduced the heritability of lean percent and run it again. Well, of course, you don't have the ability to make so much response in lean percent. And that's why we get the ellipse flattened in this way. And the selection index is still doing the best thing. So if we show the isoeconomic lines, this is the point that the index chooses. So recalling the yellow ellipse is a function of the genetics and the phenotypics of the population we've got, and the purple lines are the economics, and the combination between those 2 says that this is the best place to be economically. And this is an example of desired gains in that you might not be happy to go for a reduction in genetic change in lean percent and would prefer to be here. And of course, you can just click here in this program and that takes you there. It also shows you the relative economic weighting, which is reflected in that position on the outcome. So if we were to put those new economic lines reflected with this on here, you can see that if we decided to be in this position, or this position, it would make a relatively small difference with respect to the economic change it would make. And so there we can begin to see a circumstance where changes in relative direction for these 2 traits is actually quite possible without much damage to the predicted economic merit. We can move on from this to look at multiple traits. This is a bit of a complicated screen to look at, but we're just looking at all 2 trait combinations. In this case, not only can we be anywhere on the yellow ellipse, but we can actually forego some of the response for these two traits because we're actually trying to achieve response in other traits. But what we can do is say we want to be here, and let me fix that response for yearling weight. That's that green line there. And what happens now is we see these red ellipses which tell us that if we want to maintain our response for yearling weight on this green line, we must click within this red ellipse for these other two traits. And if you look at this or rewind and look at it again, you'll see I'm always on the green line. If I click outside, then I cannot achieve it. So this is just a way of discovering what you can achieve with this strategic desired gains approach. And it's strategic in that there are no individual animals involved here. It's a theoretical prediction about what changes can be made. Let's move on to the previous example in a bit more detail. If we were generally aiming in this direction with this index, but decided that we would either move as far as here or here, that's quite a large change in direction of genetic change. And that might be, for example, creating two different lines. If we did do that and we crossed these two different lines, we would expect to arrive here. And you can see that the difference between the response by going only for the index would be here, as opposed to going for these two lines and crossing them would be here. So little damage done economically if we decided to go back to the original direction. And this is a reflection of what happens when we've got an antagonistic correlation between two traits, as we have here, because there's a negative correlation between lean percent and number born alive, so reflected by the direction of the ellipse. However, if we were generally wanting to go in this direction up here and decided to do the same thing by dividing our attention into two different lines and then crossing them, we would see a much bigger compromise in genetic gain in terms of the original direction. And so this is an example of where a couple of traits can be manipulated for the relative direction between them with little damage. And this is something which you will see in MateCell. You will be able to make changes to some traits and combinations of traits without much deviation from the frontier. So the two ways of discovering these things is to actually go ahead and play with them in MateCell and get a feel for them. Or if you want to be more on top of it, possibly download Software Desire. And there's an alternative here, Multiple Trait Desired Gains from Julius van der Werf, and explore what sort of compromises are made theoretically before moving on to the tactical desired gains approach. Progeny Explorer is an attempt to do the same sort of thing as Desire, but using the EBVs of animals, and it's probably not quite as functional as directly using MateCell. And just to remind us, we can manipulate the trait means and other aspects such as shape in MateCell and observe the compromise that we make as a deviation that the solution is from the frontier. So far we've been looking at changes in the direction of genetic gain across traits, and now we're going to look at changes in the distribution shape. And we have in the yellow box a number of tools in MateCell for doing that sort of thing. What we're talking about is why you might do it. You might be aiming for a consistent product by reducing variation in progeny outcomes. And we've got to be careful to take account of the fact that environmental deviations and other factors will, of course, impact on the outcome. But you can manage these things to the best you can in MateCell as far as predicted genetic changes are concerned, which has some handle on the problem. Multiple markets, you might be targeting multiple seed stock or multiple product markets and looking for consistency within each of those. And you could use the target bimodality tool for that. But if you want to do this across traits, then you should look at multiple end uses in the manual. You might be wanting to do corrective mating, for example, for type traits such as foot angle and dairy cattle. You might be wanting to do assortative mating to go elite for index or elite for individual traits. And you might be concerned not to have outliers in the progeny generation. How much compromise on the frontier? Well, you can find that out for yourself by running MateCell, using different changes on the distribution shapes and different weightings for those and seeing how much compromise that you make. And now we'll move on to the last one, which is managing genetic variation for some traits. And of course the how of that is largely what we've been talking about using the trait management tool. And this is managing between family variants. If we look again at MateCell, these histograms of traits are actually due to the prediction from the matings that are being made. And when we look at differences on this scale, we're looking at differences in family means. And so that means that we're dealing with between family variation. But we do have the possibility in MateCell to also handle within family variants using the genomic mate selection approach suggested in the manual. Basically there we're looking at what the genetic marker constitution of the parents is, and we're choosing mate allocations that we're going to give typically larger genetic variation predicted in the progeny, and that's of value in the longer term in the breeding program. You could even get a bit more fancy and consider in use of your genomic EBVs and how you calculate them, and also the genomic relationship matrix and how you calculate that you could target specific chromosomes or regions of the genome in order to maintain variation for the trait effects on those chromosomes or regions. Why would we manage genetic variation? Of course, it's potentially as a prelude to splitting lines, but then in that case you might use the bimodality tool or the multiple end uses tool. But of course you may want to maintain genetic diversity for specified traits, and the main reason for doing that would potentially be to increase future genetic gains for specific traits. Well, that's us come to the end of this video. It's not quite the end, but I'm going to treat it as the end. You can leave now because I'm treating the last two slides as an appendix because they're a bit out in the wing. So if you consider EBVs for two traits and we're plotting them, and this ellipse gives some idea of where the response might be due to this single selection. But what you would consider is that there is a scatter plot of points here reflecting the EBVs of the individuals, or probably more accurately, the average of pairs of EBVs for mating pairs. But that should make little difference because the pattern of mate allocation is not going to matter, at least for the selection index. So this line here defines the selection index. We're essentially going to be selecting individuals or mating pairs to the top right, and it's as if it were focused on infinity out here. That's why it's a straight line when we want to move in that direction. I'd be careful to note that if you use tactical desired gains, what you're doing is altering the slope of that index and altering the direction without changing the nature of how you do things. That's for tactical desired gains upwards, downwards, or stabilizing tactical desired gains. However, if you're looking at a different tactical desired outcome, and that might be you want to change the shape of the distribution, for example, to make it less variable, and it's not quite the same as a single trait because we've got two traits here, but it might be a bit like avoiding matings that give you extremes here and making matings that give you values closer to here because you're aiming more or less at a focal point over here. So that might be reducing variation, setting minimum or maximum as a boundary, and those sorts of manipulations. And also, of course, bimodality, which would give you a different picture here. You would then be focusing over here and over here, perhaps. So we would end up getting a lower response because the center of gravity for this red selection would be here as opposed to for straight index selection. So you do get compromises when you change the nature of the distribution to some extent. And there is some value potentially for you to look at it in this context. Maybe you can put into this sort of a framework, at least mentally, what you're doing with these different tactical outcomes. The difference that you see here, the compromise you make in response, will be seen on the frontier, so you can manage that. This is just a different way of perceiving it. Well, hopefully that helps and doesn't complicate things too much. And that's the end of this video. Thank you for listening.